Okay, let's talk about parametric curves and areas bound by them for a second. Generally, at the end of a Calculus 2 course, a student is fairly proficient in calculating areas whenever you have a graph such as these, such as this one that I'll sketch right now. And let's say your graph, you're only allowing x to be between a and b there. And if you ever want to find areas, let's say this area right here, you generally are able to do the integral of y dx from a to b. And that's usually okay. That's usually something most Calculus 2 students are able to do, something you see at the very beginning of the course and practice throughout. But that only works if you have x is the variable here. For example, if y equals x squared, then that's super easy to calculate. You just say a to b, x squared dx. You find antiderivatives and you move on. That's fine. However, if you have x given as a function of t and y also given as a function of t, then you can't find antiderivatives here because your integral won't be dx, right? Won't be with respect to x. But with a u substitution, you can simply do this. To make a substitution, if you know, again, y is your g of t and x is your f of t, that will make dx the derivative of f prime of t dt. And so this equation will become, this equation right here will become y becomes g of t, dx becomes f prime of t dt. And then you're integrating from a to b. Right here I used alpha and beta. It doesn't really matter. All that matters is that you know that these are the bounds for t. This is how far t can go. And so I'm going to use alpha and beta just to stay consistent with the notation that I have here. So this is the area now. They're going to give you the same value. So I'm going to solve this example. Of course, you don't have to remember all of this. I think remembering the idea is important, but if you want, you can just memorize the formula, and that's fine too. If your graph is sideways, I will sometimes find the area x dy, and that's going to give me f of t g prime of t dt. So either of the two formulas can help you find the area. So let's solve these two examples. So in this first example, I'm given that t varies from 0 to pi over 2, and I'm given that x and y are these two expressions, and this is the area that I want to find. Okay. So because this looks like the traditional area from Calculus 2, like this, it looks like this one over there on the top right, then I'm going to use this first formula that I wrote. I'm going to use that the area is the integral from a to b. In this case, I'll keep using alpha and beta of y dx, which is going to be alpha to beta. So y is this is g, sine of t cosine of t. And then dx will be sine t prime times dt. And that's setting up the integral. That's all there is to it. Now I just have to solve the integral. So let's go ahead and solve it. I also have to note the limits of integration, which are 0 and pi over 2. I'm going to write that on my next line. So I'm integrating from 0 to pi over 2. This is sine t cosine t. The derivative of the sine of t is the cosine of t dt, which makes this look like cosine squared of t, sine of t dt. There are two cosines in there. Now to solve this integral, I see that it's not very complicated to note that this is cosine squared. And whenever I have sines and cosines multiplying like this, I'm always thinking in the back of my mind whether it's a good idea to use a u substitution. It seems like that's a good idea here, because if I make u equals cosine of t, then du is going to be negative sine of t dt, right? So this is going to be negative du, and this will turn into u squared right there. Okay, so my integral then will be negative u squared du. Now I have a couple of choices here on how to handle the limits of integration. I can keep them as they are, and at the end just replace u with cosine of t again and just plug in pi over 2 and 0, or I can go and say, all right, when t equals 0, u is the cosine of 0, which is 1. So 1 goes in here. And when t equals pi over 2, u is the cosine of pi over 2, which is 0. So 0 goes right there. You see that this is in reverse order. The integral is going from 0 to 1, instead from 1 to 0 instead of going from 0 to 1, which is the most traditional order here. But I can always revert the order of my integrals by just changing the sign of it. So I just revert the order, just swap 0 and 1, and then I add an extra negative outside that cancels with the negative that was already there. U squared du then will be u cubed over 3 from 0 to 1, which will be 1/3. And that is the exact area that we had up top there. The area here was exactly 1/3. Okay. That's pretty much it. I want to solve one more example now with where I use the second formula, where I use x dy instead of y dx. You should definitely write this formula down, memorize it. This is not one of the most difficult formulas to memorize because it's so similar to the ones you've seen and used in calculus too. So let me do the other example now. This is the example that I was thinking of. You look at this. Now the area is not limited by the x-axis anymore. It's limited by the y-axis. So whenever you see an integral like this, you gotta imagine you're adding those little rectangles whose heights and areas are like this. And so their heights will be x. They're not going to be y here. And so I'm not going to do an integral of y dx. I'm going to do an integral of x dy here. And even more in this problem, I have an extra problem. I have an extra issue, which is I don't know what are the bounds for t. So is t between 0 and 1, between 0 and 4? I don't know. But I can look here that these points are the points that I'm concerned about. So since this is the area that I want, these 2 points are the points that I'm concerned about. These are the points where I start the curve and when I stop the curve to be able to get this area. So these points are the points where the function touches the y-axis, which means x equals 0 at these points. So I can solve these points for these points by setting, right? Because x is t squared minus 2t, so that means that if I factor, then either t equals 0 or t equals 2, and so that means t is going to vary from 0 to 2. So this is a skill you need to have as well. And now I'm going to leave some alpha and beta here, and then I'll make my change here, my u substitution. X will be t squared minus 2t. And then dy will be the derivative of this, dt. But note that the square root of t is the same as t to the power 1/2. And also a very common mistake here is to forget that this dt needs to multiply the whole thing. This dy needs to multiply the whole thing. See here, dy was multiplying all of x. This is all of x. So it needs to multiply everything. You protect the entire expression with parentheses there. And then I'll add my limits of integration from 0 to 2 like I calculated before. All right, now everything else is just algebra. If you understand what we did so far, the rest is just training how to solve integrals, and it should be fine. Okay, so let's do it. This is t squared minus 2t. This derivative should be 1/2 t to the power negative 1/2 dt. And then I get to solve this one by distributive property, multiplying these in. I'll keep the 1/2 outside because it doesn't make a difference at all. And then I add the powers, t squared times t to the power negative 1/2. It's just t to the power 3/2. And then minus 2 times t to the power 1/2 positive. And now I anti-derive this. So reverse power rule, I add 1 to the power. Add 1 to the power. 3/2 plus 1 is 3/2 plus 5 plus 2 over 2, which is 5 over 2. And then divide by 5 over 2, which is the same as multiplying by 2/5. And then 2t. And then I add 1 to this power. It becomes 3/2. And then I divide by 3/2, which is the same as multiplying by 2/3 right here. And it's always a good idea when handling these fractional exponents to maybe derive this. Take a look real quick. When 2/3, 3/2 comes down, it's going to be 3/2 here. These cancel fine, and then I subtract 1 from the power. You get back to this. So double checking is a good idea. 5/2 comes down. There's 5/2 here. It's going to cancel. And then subtract 1. It's going to be minus 2 over 2 becomes 3 over 2, goes back to where you were. So a good idea to double check that your integral makes sense. And again, you're plugging in 0 and 2. So you're almost done here. 1/2 2 over 5 times 2 to the power 5/2 minus, and this is a 4 right there. 4 over 3 times 2 to the power 3/2. When you plug in 0, everything is going to be equal to 0, so I'm not going to bother with this at all. I think this could look a little bit better, but I don't think it's going to look great anyway, so I'm just going to simplify a little bit and then stop. So here the 2 comes in. I'm going to do that. Use distributive property with this 1/2 right here. This will be 2 to the power 5/2 over 5. As I multiply, these cancel, and then this 1/2 and this 4 become a 2 as I cancel them out. So this is what I have so far. And so maybe I'll handle it as 2 to the power 5/2 over 5 minus, so this is a 1 right here. And I'm multiplying powers of the same base. I might as well add the powers, because why not? But this is then 2 to the power 2 over 2. When I add, this becomes 2 to the power 5 over 2 over 3, which is great. Now this is the same number multiplying here, and so I get to say that this is, if I factor this number out, this is 1/5 minus 1/3. Good. So I can just use a regular common denominator calculation here, and this will be multiplying one of these by 3. This will be 3 over 15. And multiplying the second one by 5. So this is going to be -2 over 15 here multiplying. So last thing I'll write is going to be adding a negative, and then again I'll add the powers here. This is 2 to the power 1. I have to do 1 plus 5 halves, so this is 7 halves over 15. And then this is almost the answer with one issue. If you go all the way back, we were calculating areas. And areas can't be negative. And the reason for that, unless I made a different mistake in this calculation, the reason for that is generally some sort of orientation issue. The curve might be going a certain way, and I calculated it going the other way, right? For the area to be positive, we'd have to integrate the curve this way, but likely we've integrated it the wrong way. So how do we handle it? Very simple, because I know this is the only possible mistake that I could have made here in setting it up. I just go ahead and add absolute values around everything. Or alternatively, see, I didn't say that was the area itself. I can just go all the way to the end and say that the area is the absolute value of this, which is simply, maybe squeeze this in a little bit. So I can just get rid of the negative. It's always a good idea just to make sure that you go back and check each step on your calculation, but I think I'm probably correct, so I'm not going to go back and check. But you're free to check yourself. I may have made a mistake, and if I did, you're free to correct it as well. So I hope that was enough that you understood the idea behind finding areas bound by parametric curves.